This is a Eustachian tube-inspired tactile sensor exploiting pneumatics for range extension and sensitivity tuning, or ESPRESS.0. In the mammalian ear, if the pressure is not kept equal over the eardrum, which is a thin membrane, then it may become stretched, resulting in a poor impedance match between the medium the signal is travelling in, air, and the mechanism that processes the signal. To control for this, the mammalian ear includes a Eustachian tube as part of the mechanism used to keep the pressure on either side of the eardrum equal by controlling the airflow on the inside. Our design is based on the mechanical interaction between a thin silicone membrane and a tactile stimulus. Our sensor takes inspiration from the Eustachian tube mechanism and is capable of tuning the effective stiffness of the silicone membrane by means of adjusting its inner pressure. The sensor consists of channels which are linked to different positions on the silicone membrane. As the sensor meets a resistive force, the liquid moves in the connected channel. This signal can then be interpreted to infer the position and magnitude of the applied force on the membrane. This paper concentrates on characterizing the response of a single channel. The signal from the sensor may be calibrated by applying a known or measured force on the tip. As the internal pressure of the sensor is increased, the signal strength in reaction to an applied force increases monotonically. We set the tactile system 3 tasks which are important for a palpatory exam. The first was shape reconstruction. The sensor was able to detect the 2 hard stimuli with sub-millimetre accuracy in all tested back pressure states. It could reconstruct the curvature of the soft stimulus most accurately when the membrane was pressurized such that the interface itself was at its softest. The second task was stiffness identification. By constructing a low-friction springboard, we were able to tune the linear stiffness of a stimulus by simply removing or adding springs. After training the sensor on labeled data, we tested to see how well it could classify the stimulus if we presented the sensor with the springboard supported by a random number of springs. We found that by making the tactile interface softer, we can make it more sensitive to stimuli with a lower stiffness. The third task was to be able to locate and map hard inclusions in synthetic tissue. The sensor palpated a region and was capable of accurately locating the hard inclusion's shape and position when only palpating to a small depth. The soft nature of the sensor and its demonstrated ability to detect, identify, and map tactile data make it a suitable candidate for development as part of a system to carry out palpation exams for medical purposes.